Today's lesson we're going to look at section 14.2, energy requirements for the change of state. Now remember from Chem 1 that changes of state are physical changes, not chemical changes, because we're not breaking chemical bonds when we are changing the state of a substance. We're just changing how fast the molecules are moving. So when a substance changes from a solid to a liquid to a gas, the molecules remain intact. So water is H2O, whether it's in the solid form, the liquid form, or the gaseous form. The changes in state are due to changes in the forces among the molecules instead of those within the molecules. Solid to liquid. As energy is added, the motion of the molecules increase and they eventually achieve greater movement and disorder, which is characteristic of a liquid. And then if they add again even more, it's going to change from a liquid to a gas. So we add even more energy, and then that gaseous state is eventually reached with the individual molecules are very far apart and they don't interact very much at all. When we talk about these forces, we're going to refer to the intramolecular forces as the forces within the molecule, and the molecules are formed by sharing electrons between the atoms. They hold the atom together. And intermolecular forces, which is what we disrupt when we change from a solid to a liquid to a gas. So these are the forces that occur between molecules. So these are intermolecular, between the two different water molecules. The bonds that hold together the molecule itself are the intramolecular forces. Intramolecular are, of course, much stronger than the intermolecular because it actually holds the whole molecule together, as opposed to just the distance between individual molecules being affected. When we talk about the molar heat of fusion, this is the energy that's required to melt 1 mole of a substance. How much energy is required to melt 1 mole? So it's fusion. If we're going to take it to a vapor, it's called the molar heat of vaporization. The energy required to change 1 mole, molar heat, of a liquid to its vapor, vaporization. So which are stronger, intramolecular bonds or intermolecular bonds? Or forces, intermolecular forces or intramolecular bonds. And of course it's intramolecular bonds. That's because it holds the whole compound together, the whole molecule together. Which would you predict should be larger for a given substance? The delta H, or the heat of vaporization, or the heat of fusion? So which should be larger for a substance, taking it from the amount of energy required to take a mole of substance from a solid to from a liquid to a vapor, or from a solid to a liquid? And it should make sense that it's the heat of vaporization because we're pushing those molecules even further apart, going from a liquid form to a gaseous form. All right, let's take a look at this concept check. It says the unusually high value of the molar heat of vaporization of water, which is 40.6 kilojoules per mole, so it takes 40.6 kilojoules to vaporize a mole of water, so to take a mole of water from liquid to vaporization, is an important factor in moderating the temperature of the Earth's surface and results in an enormous transfer of energy to the atmosphere as liquid water evaporates as part of the hydrological cycle. It wants us to calculate the amount of heat in kilojoules needed to evaporate 10.5 kilograms of liquid water at 100 degrees Celsius. So we're just taking it from liquid water to evaporate it completely at 100 degrees Celsius. All right, so let's see if we can make this work. This is the same problem we were looking at on the previous slide. In we have 10.5 kilograms of water, and what we need to do to start off with is to change that to grams. So 1 kilogram equals 1,000 grams. So let's move this 3 times. 1, 2, 3 grams of H2O. Now what's the amount of heat in kilojoules needed to evaporate that many grams of liquid water at 100 degrees Celsius? So we know that this information is super important. This is the molar heat of vaporization for water, and every pure substance has unique values for those. So 40.6 kilojoules per mole. Well, it wants the amount of heat in kilojoules. I know how many grams of water I have, but this tells me how many kilojoules per 1 mole. So let's go ahead and take this and change it to moles. There are 1 mole is 18 grams. I'm going to put that in the calculator, 10500 divided by 18. And I have 583.33 moles of water. And if I can set it up as a proportion, or I can set it up to cancel, it doesn't make any difference. If I have that many moles of water and I know that it takes 40.6 kilojoules for 1 mole of water to be taken to steam, I should be able to just multiply that. So that times 40.6 is going to be 23,683.3 kilojoules. And the correct answer then, we would put that in scientific notation, is 2.368 times 10 to the 0.31234 kilojoules is the amount of energy required to take 10.5 kilograms of water to get it to the heat of vaporization at 100 degrees. It would take that many kilojoules. And the same situation works with the heat of vaporization and with the heat of fusion. You would just work it out the same way.